Yes.
Greetings from CSR NIST, Jorhat. I welcome all of you present online today. A very good morning to one and all present with us today in day 6 of International Virtual Workshop on Global Seismology and Tectonics 2020. First of all, a big thanks to all the participants who attended the lecture by Professor Ramesh Singh yesterday. Let's brace ourselves for another riveting session of knowledge sharing and integration today by Dr. R.B.S. Yadav, who is going to deliver a talk on Coulomb stress modeling and seismicity triggering, a perspective on future seismic hazard. Now, before we start his session, may I request our session chairperson, Professor J.R. Kyle, for his initial remarks. Over to Professor J.R. Kyle.
Thank you, Shantanu. It's our great pleasure to have Professor R.B.S. Yadav as our invited speaker today. He's a young professor, young scientist of the country. I know him since ISR days. Now he is in Kurukshetra University, and he is always very dynamic and do innovative research. And today he will speak on a very basic understanding of the Coulomb stress to understand earthquakes happening and its implications to seismic hazards. We'll be very glad to listening to Professor Yadav on this topic. Over to Shantanu, please.
So thank you very much for your initial remarks. Now may I request Dr. Sinmoy Rajkumar to introduce our guest of honor, Dr. R.B.S. Yadav. Over to Dr. Rajkumar.
Thank you, sir. Good morning to all. In today's session, we have with us Dr. R.B.S. Yadav. Dr. R.B.S. Yadav is presently working as an assistant professor in the Department of Geophysics, Kurukshetra University, Haryana. Prior to that, he has worked as a scientist at the Indian National Center for Ocean Information Services in Kois, Hyderabad, and Institute of Seismological Research, Gujarat. He has completed PhD degree in Engineering Seismology from the Indian Institute of Technology, Roorkee. He has published 40 research publications in the international peer-reviewed journals having high impact factors. He has also served as a potential reviewer of more than 60 scientific articles for international journals. Dr. Yadav has been awarded by the Young Researcher Award in 2014 by the Ministry of Earth Sciences, Government of India, in recognition of his outstanding contribution in the field of earth system sciences. He has also been granted as research grant in 2015 under DST Fast Track Young Scientist Scheme by the DST Government of India. With this short introduction, I request Dr. Yadav to start today's session. Over to you, sir.
Thank you so much for the nice introduction. I am very much thankful to Dr. Shantanu for inviting me in this talk. I am also thankful to the Professor Kayal, who has always inspiring for us. So today, just I am going to deliver my talk on the topic that is Coulomb stress modeling and seismicity triggering, a perspective on the future's seismic hazard. So basically, what is the seismicity triggering? Everybody know that if any earthquake is occurring in any place, then it will release the stress. This is our belief. But if any earthquake is occurring in any region, when it will be releasing the stress, somewhere it is increasing the stress also. And then the region which will experience the increasing stress because of the occurrences of that earthquake will be the focus of the future earthquake. And then this phenomena is basically known as the seismicity triggering. So triggering doesn't mean that it will trigger the event at a totally stress-free location. No, it is not that one. So if stress is increasing at a particular place, then what will happen basically that it will increase the stress at the location of the second earthquake that is already in the closeness of the failure. That means first earthquake will trigger only the second earthquake. So I will start the lecture with a very basic concept of the elastic rebound theory that is given by the H.F. Rad in 1906. So here we can see that if there is a fault that is having the two blocks and moving parallel to each other, so if it is locked, then what will happen? There will be no movement. But if the stress is applied because of the movement of the plate motion, then what will happen that the fault will be basically moving parallel to each other, and then whatever the linear features present on the fault, that will be also moving according to that one. So what will happen if the stress is applied stress, external stress, basically because of the plate motion, that will exceed the strength of the fault, then finally it will rupture, and then you will see the displacement. And again it will be reloaded when there will be stress is released, then again it will be reloaded for the future earthquake. So what is the basic Coulomb stress theory? This is based on the hypothesis basically that these faults will interact by the transfer of the stress. So this can be understood by simply by thinking about the stress transfer between the bricks and a spring that is shown here in the figure. So you can see this is the spring and there is the brick and there is the winch. If you start cranking this winch, then there will be that spring will be loaded and tension will be created here in this spring that will move the bricks. So there will be two kind of the forces working here. One force will work on the spring, and that force will be the length multiplied by its stiffness. That is the force working on the spring. And there will be the another force that is restoring kind of the force that will work on the bricks. Here, this will be the just multiplication of the two-factor weight of the brick and the friction working on the surface. So if these two forces are basically equilibrium in state, or both are equal, then there will be no movement of the brick. But if this force balance will be exceeded, that means if the force working on the spring will be higher as compared to the restoring force, then the bricks will be moved. And this is what happened in the case of the earthquake. And then we just have to wait for the another couple hundred of years for the winds to keep the winding and stress to accumulate, and then the another earthquake occurs. This is the phenomena of the earthquake occurrences. Now think about the different way. Now we add the another spring and the brick along with this first one. So again start with cranking this winch. Then again this first spring will be loaded. It will move the first brick that is shown here in the purple color, and then this will again load the tension inside the second spring, and that will cause the movement of this another brick. So this is the subsequent basically transfer of the stress from the one brick to the another, and that happens in the case of the earthquake. Suppose if there is a long linear strike slip fault, then you will find the similar kind of the behavior there. So this phenomena is basically known as the Coulomb failure stress, Coulomb failure criteria, and then the Coulomb failure stress can be calculated by the two factors. One is the shear stress change, and then another one is the normal stress change. So normal stress change multiply the coefficient of the friction will be added with the shear stress change, that will give the concept of the Coulomb stress changes. So what will happen if this Coulomb stress changes will be positive, then the fault will be closeness to the failure. And if this Coulomb stress changes will be negative, then it will be away from the failure. This is the concept of the Coulomb stress theory. And then very familiar with this Moore diagram that is showing the how the failure happens when the two stresses are applied, that is the normal stress and the shear stress. So this is the Moore circle, and the region that is falling in this negative Coulomb failure stress, that will be that fault will be not going to be failure. But if the fault have the position in this positive Coulomb stress, then it will be going to be failure. And there is the state that the critical CFF that will showing you that how the failure will happen, and the slope of this line that will be giving you the shear stress, that is giving you the coefficient of the friction. So this is the same thing that we have explained earlier. Stress is basically accumulated on the major fault during the inter-event time. So two events are going on. Between that, stress is accumulated because of the plate movement. So this stress changes is basically occurred because of the two process, that is long-term tectonic loading, and then there is the post-seismic displacement. So this formula that we are seeing here, that is delta CFF is delta tau slip plus mu delta sigma n plus delta p. Here delta p is the pore pressure. This is another factor that is influencing the Coulomb failure stress. But if you combine this pore pressure changes with the mu, then you find the apparent coefficient of the friction. That is this formula is similar to the previous one. So here again, if this delta CFF is positive, then you will find that the fault plane will be loaded, and if it will be negative, then it will be under relaxed situations. So again, we have seen that the stress earthquake occurs when the stress is the strength of the fault, and then we can quantify this effect of the stress in the form of the Coulomb failure stress function. So basically, you can see that the Coulomb failure functions, if it is sometime exceeded value of 0.1 or 0.1 bar, or sometimes it is 0.01 bar also, then it will increase, it will cause the failure of the fault. So this is the graphical representation how the Coulomb stress changes is basically calculated. So first we calculate the shear stress changes. Suppose this is a fault that is moving because of the tectonic loading, and there is the fracture in this fault, the failure of this fault, and this is the basically the receiver fault that is receiving this stress. So shear stress changes, you can see the positive shear stress you will find along the both the ends of this fault, and then you multiply the two things, friction coefficient and the normal stress changes, and then you are getting the Coulomb failure stress. So basically in the normal stress changes, basically coefficient of friction is basically very important, and this is controlling the behavior of the normal stress changes. So Coulomb stress changes is calculated basically by the two approaches. One approach is called the specific receiver fault. So there is one fault that is called as the master fault, which is basically rupturing during an event, and another one is the receiver fault that is receiving this stress. So master fault will have the slip, but for the receiver fault there will be no slip. So that receiver fault will just receive the stress from the master fault. So here you can see this is the master fault that is going to be slip during an event, and then this is the receiver fault that is parallel to this master fault. So this is the shear stress. This is again the same concept as we have seen earlier, and then you can see how the Coulomb stress changes will be varying if the master fault and the receiver faults having the similar nature. So you know that a specific receiver fault having the definite strike, dip and rake, and it has the no slip. So there is another concept that is optimally oriented fault plane. So these are the planes basically which got the maximum resolved Coulomb stress. And then these OPs are basically controlled by the two factors. One is the post-seismic stress that is released by the main shock. If main shock is happening, rupture is happening, that stress will be controlling the OP's direction. And then the another one is the regional stress, and this basically regional stress is governed by the plate motions. So post-seismic stress changes that will affect the very near patches of the main shock rupture, but the regional stress this will affect the more away from the main shock rupture. So this OP is basically controlled by the two factors, post-seismic stress and the regional stress. So you can see in this picture how the Coulomb stress changes. As you see in the previous master fault, the master fault is same, but if there is this is calculated on the optimally oriented fault plane whose the regional stress is working the north 27° east direction, then this Coulomb stress changes pattern will be just different than we have seen the earlier. So these are the two basically approaches, and this approach that is optimally oriented fault is basically used for the interactions to see the interaction of the main earthquake, main shock with the aftershocks, and the fault approach is basically done for the long-term interaction of the two major earthquakes. So we will see the some examples how the Coulomb stress changes will be different in the different conditions. So this is a kind of the example of the vertical right lateral fault. So here you can see that this is the master fault and the receiver faults having the different orientations and different geometry. So here the master fault is same in all the conditions, but the receiver fault is different, having the strike parallel to the master fault. Then this will be the Coulomb stress scenario. And if this master fault is same, but receiver fault is the kind of the thrust fault, then you can see that the stress pattern will be changes. Then this is again the thrust fault, receiver fault is thrust, but it is perpendicular to the master fault. And then you can see that how this stress is basically changing. And if this is again the same master fault, but the receiver fault having the different inclination, different geometry, then you can see that how this Coulomb stress changes is basically working differently. So basically Coulomb stress changes will be according to the receiver faults. This is the similar thing that if a person having the different capability to bear the stress, similarly here the different faults have the different characteristic to receive the stresses. Now this is the kind of the thrust faulting that continental reverse faults, but this scenario is different. One is the surface cutting fault and another one is the blind fault. So how the stress will be changes. So fault that have the surface stress having the major drop in the stress in the upper crust, and there is the stress increase here inside the down dip direction. But if it is the blind thrust fault, you will see that the constances of the stress on the end of this rupture as well as the another side of this fault. So this both type of the reverse fault promote the reverse rupture along the end. So sometimes these stresses that is on the upper side of this fault that can generate the secondary and that can rupture the secondary fault. And this kind of the example you can see the North Ridge region, where in 1994 6.7 earthquake has occurred because of the rupture of the Hector mine earthquake. So this is the another sections that is at the end of the end of the fault rupture. And you can see that in all the scenarios, the stress is basically high. So basically in the thrust kind of the fault, you will find the different kind of the distribution of the these aftershocks. So it is a kind of the diffuse, but if it is a kind of the strike slip fault, you will find a very good correlation with the aftershocks location with the fault. But in the case of the thrust fault, you will find the aftershock distribution is diffuse, and this is because of the diffuse nature of the Coulomb stress in the blind thrust fault. So this is another characteristic of the Coulomb stress. If there is the fault that is having the nature of the thrust, but this fault rupture length and rupture width are similar, that ratio of length and width is same, that is the square kind of the fault, then you will see that this will show a kind of the butterflying wings, and you will see that the positive stress is more dominant as compared to the negative stress. So stress is important in the form of the butterfly wing, but if this ratio is much larger, that means length is much larger as compared to the width, then you will find that the stress decrease region, that is the decrease region, will be much more dominated as compared to the stress increase region. So this is the behavior of the two faults if the rupture length is different. And then this stress important to wings that will be promote to rupture of the strike slip faulting, but somewhere it is the thrust faulting will occur just at the end of the this fault, but mostly it is promoting the strike slip fault. Then the triggering of the thrust earthquake on the adjacent patch of the similar size along the strings. So it is the same kind of, this is the square fault, but it will receive about 1 bar stress over the 70% of the adjacent fault. So here the short thrust ruptures are basically efficient to triggering the other thrust event of the similar size along the strike of the rupture plane. So for the square fault, that will find 70% of the adjacent patch will experience the increase of the stress. But if it is the long ruptures are basically efficient to inhibit the thrust fault in the larger region that is perpendicular to the rupture planes. And very less amount of the positive stress will be received by the adjacent patch, and that is only about the 50%. This is a typical example of the North Anatolian fault. So here progressive failure of the North Anatolian fault has been shown from the 1939 to 1992, and then it is a typical example of the stress triggering. So you can see the example here of how the one earthquake is basically transferring the stress to the another earthquake. So from 1939 to up to 1999 and 1992, it has been modeled. And in the last figure, you can see that this is the region that is the Seismic earthquake, and it was very well identified region of the high stress, where in the 1999 about 7.4 magnitude earthquake was triggered, and this is the successful story of the earthquake triggering. So we can identify the location of the high stress or the future earthquake, but you cannot predict the amount of the rupture. So how much amount of the rupture will be there, that we cannot predict, but the location we can identify where the future earthquake will occur. Then from the stress changes, now we can see the how the probability of the earthquake will increase. So if suppose this is the fault rupturing, and at the end there is the point X, so how it will receive the stress. So we have seen earlier this patch will receive the higher stress, and then if we see the Coulomb stress changes versus the time graph. So if this event has could not happen, then this is the timing of the basically occurrences of the future earthquake. But because of this earthquake, this time has been advanced. That means it has triggered the event. And then the probability of the occurrences of the future earthquake will basically increase. So this is the transient increase, that means it will start time, but you will find that there will be some permanent increase in the seismicity level in the region because of these stress changes. Now I will show some example of the stress triggering in the Indian regions. Application of Coulomb stress modeling for some recent seismic sequences in the northwest Himalaya. I have chosen basically 4 earthquakes for the magnitude greater or equal to 6.5 occurred during the year 1991 to 2005. These earthquakes are the 1991 Uttarkashi earthquake, then 1997 Pakistan earthquake, and then the Chamoli earthquake happened in 1999, and then the recent 2005 Kashmir earthquake. These earthquakes are chosen because we will get the reliable rupture parameters and focal mechanism as well as the aftershock distribution. So this is the Coulomb stress changes for the October 1991 Uttarkashi earthquake. So the rupture parameters have been estimated. Basically, we estimate the rupture length, rupture width. Either you can use the empirical formula or it is already given. So I have estimated this rupture length and width from the Wilson Copper-Smith empirical formula. Slip has been important in the and it is resolved in the reverse direction and the right lateral directions. So, and then you can estimate the up dip and the down dip edge of the fault rupture. So this is the Coulomb stress changes at the epicenter, at the hypocenter of the earthquake, and this is just above the hypocenter of the earth. So you can see that the most of the aftershocks are occurring at the up dip edge, and this is the cross section. If you take the perpendicular cross section, you will find that the most of the aftershocks activity basically occurred at the up dip edge of the fault rupture, and that is basically triggered by the high stress Coulomb stress. So you find a very good correlation between the epicenter location of the aftershocks and the positive Coulomb stress that is basically supporting the earthquake triggering mechanism. Then for the 1997 Pakistan earthquake, the similar things we calculated the different parameters, and then we have seen the Coulomb stress changes at the hypocenter as well as the deeper in the depth. So if we take the cross section perpendicular to this, we'll find that the most of the aftershocks are occurring in the down dip edge of the up dip edge, but it is much more deeper in the section. And this is the maximum Coulomb stress that is resolved up in the region. So here again we find that the maximum stress is basically occurring that is triggering the aftershocks activity. Then we have calculated the Coulomb stress changes for the 1999 Chamoli earthquake, and again we found that if you see the cross sections, we found that the most of the aftershocks are occurring at the up dip edge of the fault, and that is supporting the triggering mechanism. So if you see the Uttarkashi earthquake or Chamoli earthquake in the Himalaya, basically you will see that the aftershocks are occurring at the up dip edge, and this is because of the slip. We can say that slip is basically propagating at the up dip edge side, and that is triggering the aftershocks. And then we have calculated the Coulomb stress changes for the 2005 Kashmir earthquake. Here we have seen the cross sections, and we find that the most of the aftershocks are occurring deeper in the deeper in the crust. So here we can see that the source is much deeper here. So maximum oxygen lying in the high Coulomb stress load below the updip edge, and that is supporting the triggering mechanism. And here the sleep, basically we find that very basically down dip edge has the lack of the aftershock activity that suggests the propagation of sleep in the updip directions. So now this is another event that happened in the Talala, Gujarat, 2007 earthquake. That seismic sequence has generated more than this 1300 earthquake of magnitude more than the 5, and just we have taken only 325 earthquake which has precisely located there. So this seismic sequence basically consisting the four shocks that is shown here in the form of the that square, and then the main shock and then the aftershocks. So first foreshock occurred here, then the aftershocks occur here, that is in the northwest direction, movement of that main shock, and then again the aftershocks was here. So you can see that this is the foreshock, this is the main shock. Main shock happened in deeper in there, but aftershocks is occurring just above inside the crust. So we have seen the static Coulomb stress changes, and we have seen the triggering of the aftershocks by the 2007 earthquake, and we found that the off-fault triggering mechanism is happening here. And if we take the perpendicular cross sections along the foreshocks, we'll find that the most of the aftershocks activity happened in the region of the high stress. So static Coulomb stress changes due to the post-seismic sleep of the main shock enhance the basically off-fault aftershocks occurrences. When the stress were resolved on the cross section, you can see here the stronger aftershocks happened here. That is basically triggering the aftershocks activity. Then there was the event that happened in 2011 of magnitude 5.1 in the same region, but it is away 8 kilometers away toward the southwest direction of the 2007 earthquake. So that was the 2007 earthquake shown here, but that recent 2011 earthquake happened toward the southwest direction. And then we have seen whether the triggering of this 2011 earthquake because of the post-seismic stress and post-seismic stress transfer by this 2007 earthquake. So this is showing the post-seismic stress, and this is showing the post-seismic stress after the 4 years of the occurrences of the earthquake of the 2007 earthquake. And then we found that this is the location of this 2011 earthquake that is lying in the high stress region, and that is showing that this earthquake may be triggered by the transfer of the Coulomb stress by the 2007 earthquake. So we have seen also the triggering of this aftershocks by the 2011 earthquake, and this three-dimensional picture of the Coulomb stress changes clearly shows that all the aftershocks are basically occurring in the high stress region, and different cross section at the different depth shows this aftershocks activity happened on the high stress region. And again, if we take the cross sections perpendicular to the rupture plane, we found that the most of the aftershocks activity of the 2011 Talala earthquake is basically triggered by the stress transfer. So you find a very good correlation of the observed aftershocks activity and the high stress that is supporting the triggering mechanism of these events. Then we have again taken an example of the Pakistan earthquake that happened in 2008. The main shock having the magnitude 6.4. This sequence having the different nature. One foreshock was there of the magnitude 5.3, and then there was the two main shock that is kind of the doublet occurred on the on 28 October and 29 October. So here we have calculated the B value and the P value, and then they forecasted the seismic aftershocks basically, and we find that the forecasted aftershocks activity is in good correlation with the observed one. So we have seen the triggering mechanism from the foreshock to the main shock. This is the foreshock, and then we resolved these stresses, and we found that the first main shock of magnitude 6.4 was occurring on the high stress. And if you take the cross section perpendicular, you'll see that this main shock was basically occurring in the high stress, and that is showing that may be triggered by the foreshocks. And then we resolve the Coulomb stresses by the combining foreshock and the first main shock, and then we find that the second main shock, that is the doublet, has triggered by the transfer of the Coulomb stress. And if you take the cross section, we see that the hypocenter is lying in the high Coulomb stress region. So again, we combined the three earthquakes Coulomb stress changes, that is the foreshocks and two main shocks, and then we correlated the location of the aftershocks with the Coulomb stress changes, cumulative Coulomb stress changes, and then we find that the most of the aftershocks activity lying in the positive Coulomb stress, and this aftershocks activity may be because of the transfer of the positive Coulomb stress of these earthquakes. So this is the typical example of the triggering of the aftershocks. And then we did these static Coulomb stress changes for the 2011 Barn earthquake that happened in 2011 of the magnitude 7.2. More than 4,000 events has been located here precisely, and then if we calculate the B value pattern, we find that the main shock happened in the high B value. That means stress, low stress region. You can see that this fault can be very easily identified on the cross sections, and the most of the region in the both side of this fault is showing in the low V value region. So aftershocks are occurring here low V value region, that means showing the high stress region. So if you do the 3D modeling of this V value, we find that the upper part of this region is basically under the high stress, that is showing with the low V value, and the lower portion having the high V value, that means stress has been reduced here. So if we calculate the Coulomb stress changes, we find a butterfly pattern that we have seen earlier, because this is the end of the thrust fault, and then we can see the butterfly pattern. And if you see that the aftershocks locations, we find that the most of the aftershocks are lying in this positive Coulomb stress region. And if you take the cross sections, we'll find that most of the 90% earthquake aftershocks are basically triggered, are lying in the positive Coulomb stress region, and then we can say that these are the triggered event by the transfer of the Coulomb stress. Then we have done the Coulomb stress changes for the recent 2015 Gorkha, Nepal earthquake, and this is a very typical earthquake that happened recently in the Himalaya. This is the location of the aftershock. This is the location of the main shock that happened at the western part of this patch, and then the largest aftershocks was happened here. So this sequence is comprising a two kind of the sequence here. This is because of the main shock, and that again because of the occurrences of the largest earthquake and largest aftershocks of magnitude 7.3. This activity that increases. So we assess the B value that is less than the 1, suggesting the tectonic origin, and then the less than 1 P value suggesting that the region is dissipating energy very slowly, and then the aftershocks will be continued for longer duration. So if you see the main causative fault of this earthquake, that causative fault was the main Himalayan thrust fault that basically shown here, and this is the red patch that is showing the slip because of the Mensa. So if you see the strike and dip of this fault geometry of the main Himalayan thrust well, this is strike to 69 degree, dip is 10 degree. So this is the location of the after activity, and this is the location of the previous background seismicity. So because of the occurrences of these two earthquakes, the activity has increased in this region. So we have taken the variable slip model of the given by this et al. 2015, and we find that the second after this largest aftershocks happened in the no seismic slip patch. So this is the place at the slip decept region towards northeast of the main south rupture. So we have calculated the Coulomb stress changes, and here we consider the receiver fault as the MST. So this is the Coulomb stress changes by the main sub, that is 7.9 Kurukshetra earthquake, and we can see that the region where the slip has been occurred, that region is showing the basically low stress, and the surrounding region is showing the high stress. And this is the typical region where the largest aftershocks happened of magnitude 7.3. So this is the combined Coulomb stress changes by the main shock and the largest aftershocks, and we can see that after the occurrences of the largest aftershock, this region again release the energy and basically showing the low stress. Then we have assessed the possibility of the mega thrust earthquake in this region in the future. So we found there are basically 3 earthquakes happened in the history in this region. That is the 1255 of magnitude 8.5, 8.5 magnitude, and the rupture dimension of this 1255 earthquake was comparable to even longer than the 1934 earthquake. Then the 1833 earthquake that have the similar rupture that's happened in 2015 during the Kurukshetra earthquake, and then the third one is the 1934 earthquake. So these 3 earthquakes happened in this region. So if you see the return period of this kind of the earthquake, that is magnitude greater than 8 in this region, so Bollinger et al. Have been found the return period between the 715 and 870 years, and based on this and the conditional probability approach, we find the probability in these 3 regions, that is the Lamchandra area, then the Lalitpur, and then the Dulakha area. So low probability of mega thrust event is basically possible in the region of the Dulakha area, because this region has recently happened an earthquake of 1934, and then the high probability of the mega thrust event will be happened in the Lalitpur and the Lamchandra. So these are the locations where the future earthquakes may occur. So we assess the seismicity rate changes in the next 10 years based on the Coulomb stress changes and the rate and state friction model. So our models show that due to the stress perturbations induced by the Kurukshetra earthquake and its largest aftershocks, seismicity rate will decrease in the rupture patch. So you can see that in the rupture patch, seismicity rate may be decreased, but these are the regions where the seismicity rate may be increased, that is the Lamchandra, Lalitpur, and the Dulakha region. So if you apply the BPT model, Brownian passage time model, and you calculate the conditional probability and take the effect of the stress changes, then this probability will increase because of the changes in the stress. So this probability from 6.3 to enhance the 24%, and 2.4% will enhance the 11%. Then we have calculated the Coulomb stress changes on optically oriented fault plane, because if you want to correlate the aftershocks activity with the high Coulomb stress region, so we calculate the stress changes on optimally oriented fault planes. So we have calculated at the different depths, 10 kilometers, 15 kilometers, 20 kilometers, and then we have taken the maximum Coulomb stress. So our model basically shows that the many smaller aftershocks may take place on the secondary part above and below the MST. So you can see this is the region, that is the off-tip region, where the Coulomb stress changes are high, and this is the down-dip edge, where the Coulomb stress changes are high. So then further, we have calculated the background seismicity rate on the basis of the past seismic activity, and background seismicity basically found to increase here in the Tibet region, and the basically at the end of the rupture plains. And we forecasted the temporal seismicity. So temporally forecasted the seismicity rate based on the background seismicity and the rate and the state friction models. So you find a very significant rate increase around the sleep pass. So the region has got a very significant rate increases, and if we take the average ratio between the this forecasted seismicity rate change and the background seismicity rate, this is showing how much percentage, how much ratio it has got increased. So on average, if you find that in the first year, the post-mains of it is still higher, 2.5 times higher than the background seismicity. And even for the first decade, we find that there is increase in the seismicity rate. So at the decadal scale, our model shows that the average seismicity rate will be close to the background seismicity rate, but still it is higher than the 30%. So then again, we have assessed the Coulomb stress changes for the very recent earthquake, 2016 Imphal Manipur earthquake. This earthquake was located 29 kilometers west of the Imphal and having the maximum intensity 7, that caused about 20 fatalities in India and the Bangladesh, and more than 100 were injured, and several thousand buildings were got damaged in the Manipur region. So this is the location of the Manipur earthquake, and this is showing the typical fault plane solutions of the given by the different agents. So you find that this earthquake was having the static slip motion, and in nodal plane 1 having the distal fault, while the nodal plane has showing the sinister fault. So what were the causes of this earthquake? So basically there are different models that shows the causes of this Imphal earthquake. So according to the Coulomb and the Kundu, and then the Coulomb in 2016, this earthquake was occurred on typically interslab region. So this is the typical interslab earthquake occurred within the predominantly northwest moving subducting slab. Then the another model that is given by the Rajendran, and this is shows that this is resulted from the north-northeast, south-southwest directed horizontal convergence and the slab bending force that dominated the plate point. Then the Singh et al. In 2007 given a different model, and they shown that there are the intersection of these three faults, that is Copley faults, Dauki fault, and this is the Burmese fault. And this earthquake happened on the basically on the Copley fault due to the interaction of these three kind of the faults. So for the calculating the Coulomb stress changes, we have taken the variable slip model of the Singh et al. 2016. So we observed that the maximum slip happened of about 0.8 meter, and then the rupture duration was 10 seconds. So this variable slip model has been used to calculate the Coulomb stress changes. So here we have taken the different kind of the receiver faults. So there are the three receiver faults here we have taken. One is Copley fault, another one is Dauki fault, and then then this is the Kurukshetra fault, CMF fault. So if you take the Copley fault, that is having the nature this one, that is a kind of the right lateral strike slip fault. So we resolve the Coulomb stress changes and the different depth, keeping coefficient of friction as same as 0.4 for the strike slip earthquake. So we found that in the different depths, this fault is receiving basically the higher stress. And if you take the maximum Coulomb stress changes in deep depth range from 10 km to 50 km, the maximum stress basically is shown here, and it is found that the maximum part of this fault is receiving the Coulomb stress changes. And if you take the receiver fault as the Dawkey fault, the stress changes are shown at the different depth here. But here it is observed that this Dawkey fault basically is not receiving the higher Coulomb stress changes. And then the another one is Kurukshetra fault, that is CMF, having the characteristics similar to the Copley fault. And depth is we have taken 0 to 50 kilometers. So again here, this fault is basically receiving this higher stress. So maximum Coulomb stress changes shows the butterfly pattern, you can see that. And then the main conclusion is that the Copley and Kurukshetra fault received the higher stress due to the rupture of the Imphal earthquake, and therefore these possesses the higher hazard in the near future, while the Dawkey fault did not receive the increased stress. Then we have calculated the Coulomb stress changes on optimally oriented fault. Again, the optimally oriented fault is basically, we know that it is controlled by the co-seismic slip and then the regional stress that is governed by the plate motion. So we have calculated the maximum Coulomb stress changes as well as the mean Coulomb stress changes between the depth 35 to 70 kilometer. And we can, because we could not get the aftershocks of this earthquake, so we plot the regional seismicity happened after that earthquake, and we found that the most of the aftershock regional seismicity, not say the aftershock, regional seismicity is falling in the positive Coulomb stress. So on the basis of this stress calculation, we were able to forecast the seismicity rate. And for the forecasting of this seismicity rate, we need the background seismicity rate, and the rate changes resulted from the Imphal, that is the stress changes. So how the background rate can be estimated? It is basically estimated on the basis of the past seismic activity, past seismic catalogs that is updated by me for the period 1964 to 2015 of magnitude greater than 4.5. So we calculated the background seismicity rate, and we find that the region of the Imphal earthquake is not having at the location of the high background seismicity rate. So we are able to forecast the seismicity rate because of this earthquake, and for the 1 year and then for the next 1 decade. So we found that there is the increased seismicity rate near the fault rupture plane for the next one year, but we could not found that the seismicity rate will increase after the 10 years. So there is no increase in seismicity rate after 10 years. So for the 1 year, there will be increase in the seismicity rate. Then we have assessed the post-seismic as well as the post-seismic Coulomb stress changes for a very well-known earthquake, that is 2001 Bhuj earthquake. So this is the typical location of this earthquake in the Kutch Rift Basin, and this is the seismic activity that is happened after that earthquake. You can see that. So this region is experiencing a very seismic activity in the northwest direction. So and if you see the regional seismicity after that earthquake, that is from 2001, so you find that not only the Kutch Rift Basin is having the increased seismicity, but also this is the Saurashtra region which is experiencing the higher seismicity rate. And according to Rastogi, this region, this seismicity may be triggered by this by the transfer of the post-seismic stress from this 2001 earthquake. So for the calculation of the post-seismic and post-seismic stresses, we have considered the velocity and density model given by the Mandel and Kojo. So this layer structure has been considered for the calculation of the post-seismic stress, and then we have considered the earth model. So earth model here, that is the rheology basically. So we considered the two kind of the rheology. Elastic crust has been considered as the elastic for the crust, that is 34 kilometer, and then the below mantle behaving as a viscoelastic in nature. But we can also consider the crust, upper crust as the elastic and the lower crust as elastic, viscoelastic in nature. So considering this earth model and the velocity model, we calculated the post-seismic and the post-seismic Coulomb stress changes for this 2001 Bhuj earthquake. So you can see the post-seismic Coulomb stress changes here and the post-seismic Coulomb stress changes at the different depth, 5 kilometer depth, 10 kilometer, 50, 20, 25, and the 30. So if you see the post-seismic and post-seismic changes, we can identify that post-seismic changes got the higher increase in the stress as compared to the post-seismic, and that is suggesting there is the viscoelastic relaxation in the lower crust and the upper mantle. So if you see the some upper part, that is the 5 and up to 10 kilometer, you find that there is the increase in the Coulomb stress basically in the east directions as well as in the northwest directions and along this direction also. But if you go deeper and deeper, we will find only two directions of the increase of the stress, that is in the eastward and the northwest. And the northwest part has much more higher stress. And this is the location where the mostly aftershocks are basically occurring in this time. So we correlated the few aftershocks with this Coulomb stress changes, and we find that the northwest part of this region is basically experiencing the higher stress. So there is a good correlation of the observed seismicity and high stress, that is again suggesting the triggering mechanism. And we have also found that there is a progressive extension of the location of the aftershocks toward the eastward also. So then there was another earthquake, largest aftershocks you can say, or largest earthquake happened after 2001, that is the Ngedi earthquake after the 5 years of this 2001 Bhuj earthquake. And then we resolved the Coulomb stress changes on the optimally oriented for the receiver fault, basically like the Ngedi earthquake, that is strike slip fault. So this is for the thrust receiver fault, and this is for the strike slip fault. And then we can see that the location of the Ngedi earthquake was basically occurring in the higher Coulomb stress region. So this may be again triggered by the transfer of the stress. One very important thing is that this region, that is the Saurashtra region, has experienced the higher stress in terms of the strike slip motion, and most of the earthquakes like happened in the Talala, that is the nature of the strike slip. So this may be triggered by the transfer of the Coulomb stress. Then we have seen the fault interactions in a Mokin segment of the East Kunlun fault, and here we have estimated post and inter seismic stress changes. So we again taken the velocity model from the different published papers, and then we have seen the progressive failure of this fault, and we can see that basically the region of this mucking is basically found at the higher stage. So if you see the tectonic loading here, and then this is the post-seismic stage, and this is the post-seismic stage, you find that compared to the post-seismic stage changes, the post-seismic viscoelastic relaxation process has played a very important role on the stress accumulator at the segment. And then we have seen the sensitivity analysis of the different parameters. So we have changed the coefficient of friction from 0 to 0.8 and changed the viscosity of the lower crust, and we found that the normal stress changes are basically almost equal to 0, and most of the Coulomb failure stresses is mainly controlled by the shear stress changes. And here the lower viscosity leads to the higher stress accumulation due to the fact that the lower value of viscosity make the process of the post-seismic viscoelastic relaxation more rapid. So here again we see that the post-seismic Coulomb stress changes at the Markov region is higher, and this is the location of the future earthquake. So finally, I will conclude my lectures that there is the possibility of triggering of the regional seismicity due to the transfer of the increased post-seismic and post-seismic Coulomb stress changes because of the occurrences of the earthquake. And these stress changes can be useful to understand the different kind of the earthquake process, how the earthquake is basically happening in the region, that can be understood by the these Coulomb stress changes. And then the geological characteristic of the crust and upper mantle can be understood by this Coulomb stress changes. And we have seen this seismicity rate forecasting basically can be possible by the stress changes. So seismic hazard can be done. And then very recently some researchers are doing the time dependent probabilistic estimate for the seismic hazard because of these Coulomb stress changes. So Coulomb stress changes can increase the possibility of the earthquake occurrences, and then it can increase the hazard in the region. So result may be sometimes suffered by some limitations, like the local effect produced by the oversimplified fault geometry. So we take the very simple fault geometry, but this is not the reality in the nature. So this can cause the problem. And then the uniform slip distribution. Sometimes we have take the very uniform slip distribution and do not take the variable slip model, that can also lead the problem in the region. Thank you so much. Hello.
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 Hello, Shantanu.
Thank you, Dr. Yadav, for your interesting talk on Coulomb stress change that can help to understand the earthquake interaction processes, seismicity triggering, and play an important role in assessing the future seismic hazard of any region. Thanks a lot. Now, may I request our session co-chairperson, Dr. Surapura, for his remarks. Over to Dr. Surapura, sir.
Thank you, Shantanu. We just had a wonderful lecture by Professor R.B.S. Yadav on Coulomb stress modeling. He has touched upon the entire gamut of stress modeling, right from dislocation model, which is the prime input for seismic hazard assessment. And in a process, he has touched upon exactly what the model should be. That means to start with, we have to have a particular fault length. That particular fault length may be assessed as the primary fault, and the primary fault gives a dislocation and the subsequent slip rate, And those inputs embedded with a good crustal velocity model that comes to give us exactly what is the stress model or the stress pattern through Coulomb stress modeling pertaining to a particular earthquake. And in a process, this also gives us an chance to assess the future seismic hazard. That means ultimately this modeling leads us to another model where we can assess the seismic hazard pertinent to that particular region where that particular earthquake occurred. So in that, with that brief remark, I really congratulate Professor Yadav for nicely enlightening us. There is a question and answer session. So I just hand over the mic to the platform to the Dr. Santanu Borua. Thank you.
Thanks a lot for your initial remarks. Now may I request Dr. Coulomb for question and answer session. Over to Dr. Coulomb.
Thank you very much. Thank you, Yadav sir, for your informative talk and the way how you have demonstrated the hazard assessment and stress modeling. So I'll proceed for the question and answers. Definitely, there are a few questions. Someone has asked about what are the conditions under which high angle reverse fault or low angle normal faults are activated. Am I audible, sir?
Hello.
Hello. Am I audible?
Hello. Yes.
Yes.
Can you repeat again?
Yes, sure, sir. What are the conditions under which high angle reverse fault or low angle normal faults are activated?
Yeah. There are the several conditions, but mainly the sleep will be responsible. So, if there is a sleep happening in the high angle reverse fault, that will uh, basically activate that Coulomb stress changes. So mainly the sleep will be responsible for the this one. Next one.
Can we do this kind of study with smaller to moderate size earthquakes or in region where only smaller to moderate earthquakes are occurring, such as Indo-Gangetic Plains or Delhi NCR region?
Yeah, you can do, as I have shown in my lecture, that we can do this for the moderate earthquake also, or even a smaller earthquake also. But the amount of stress will be basically small. So, but we can do. There is a possibility that we can do in the Indo-Gangetic Plain. But for that, we have to very precise fault plane solutions, rupture parameters, and everything. If it is there, then you can do for the any region. No problem.
And somebody has asked about how can we distinguish aftershocks from background seismicity?
Oh, this is a very nice question. So basically, after shocks, when main shocks happen, this will elevate the after shocks. So there is a series. Before that, there is the four shocks, then the main shock, and then the after shocks. Before that, seismicity rate will be the main thing. So if we assume the background seismicity, that is because of the D cluster catalog, you can estimate the background seismicity. And when the any main shock happen, then you will find the aftershocks, and that will elevate the activity rates. So by this we can distinguish the aftershocks and the background seismicity.
The next one is like the geometry of the MHT in the Himalaya vary
Hello.
from one second. How it will influence the Coulomb stress changes and occurrence of hello, sir. The of MHT in the Himalaya vary from one second. How it will influence the Coulomb stress changes and the occurrence of earthquakes.
Yes, it is. It is evident in the Himalaya that MST in the northwest Himalaya and the northeast and the middle part, it is changing. So geometry is very important, as I saw you earlier. The deep directions, rake, and everything that everything will be affecting the Coulomb stress changes. Your rake is changing, that will affect our geometry will changing, that will affect the Coulomb stress changes. So you will not find a similar kind of the Coulomb stress changes in the northwest Himalaya, in the middle Himalaya, or in the northwest Himalaya. So certainly this MST geometry will affect the Coulomb stress changes. Yes.
Okay, sir. Dr. Anup K. Suttar is asking about what is the minimum amount of stress changes required to trigger an earthquake greater than 6 magnitude?
Yeah, it is very nice question. So actually the answer is that there is no required minimum stress. Any stress, as I told you, that the triggering will happen at the any kind of the stress level. So it will be 0.1, 0.01 or 0.001, any kind of stress. Main thing is that how the fault is behaving. If the fault is already under high stress, then it will trigger very soon. If it is not under high stress, then it will take longer time to activate or to trigger. So only it can delay, the amount can be delayed, but any amount can trigger the earthquake. So that amount cannot be defined. Okay.
Okay, so another one is from Deepjyoti Goswami. He's asking that does earthquake in a master fault activate nearby non-optimally oriented faults due to stress rotation?
Hello. Hello.
Does earthquake in a master fault activate nearby non-optimally oriented faults due to stress rotation?
Uh, okay, earthquake in the master fault activate nearby non-optimally oriented fault due to this. I couldn't understand this question.
Okay, sir. Shall I
What?
proceed for the next one, please?
Yes, please. Yes, please. Proceed for the
Okay,
next one.
so Dr. Arun Prasad is questioning about, is it possible for a small 5 magnitude earthquake to trigger series of moderate size earthquakes? Is it possible to trigger that much with a small magnitudes?
Yeah, it is possible. As I told you earlier, that any amount of the stress level can trigger the earthquake. This is mainly depending that the how the receiver fault is taking. So if it is already under high stress, so a small earthquake can also be triggered that one. So this is possible.
Okay. Then other is, can normal faults trigger thrust fault earthquakes? A normal fault being the source and the thrust being the receiver faults?
Yes, this will be depending upon the slip direction, and also yes, it can be triggered, no problem, that can be triggered, but depending upon the slip geometry and focal mechanism, everything, if it is favorable, so it can, the normal fault can also trigger this one.
So the next one is, do you think that Coulomb stress change study can reveal the importance of future large size earthquake studies? As we see that all of the studies were done for the some large size earthquakes, and then the aftershock is correlated with the stress pattern. Please comment on that.
Oh, the question is that Coulomb stress changes study can reveal the importance. Yes, several studies has been done where the large earthquake, as I have shown you, the North Eltonian fault, there is the interaction of the large earthquakes. So that study is basically being done at the several places, and the interaction process is being understood. So one earthquake is basically triggering to another earthquake, and so it is possible to basically understand the mechanism of the earthquake occurrences. Yes.
Okay, so sir, I had the last question. It was from Deepjyoti Goswami. Sir, have you incorporated fault healing rate in the latent state frictional model? Have you determined the frictional parameters from laboratory experiments?
Laboratory, yeah, that some parameters are already given, like the A sigma, that is a very important stressing rate, basically, that is already given, and that we have incorporated from the laboratory experiment also. So it is some parameters already given, only the stress changes, and the region is basically affecting this seismicity rate for rate changes. So yes, laboratory experiment parameters has been incorporated there.
Another one is come up. Shall I read it out, sir?
Yeah.
Sir, how can we explain the presence of aftershocks in the shadow zone during Coulomb stress changes calculation? Present associated with the primarily assumption of shear modulus and the effective coefficient friction.
Yeah, you can find that there are some aftershocks lying in the stress shadow region. That this is because of there are several uncertainties involved there. So if you are using the slip distribution, using the geometry of the fault. So if slip distribution is not accurate, or you are using a very uniform slip, not using the variable slip, then again your stress calculation will be not good, and therefore you will find that some of the shocks are occurring on the stress side of region. Okay.
Yes, sir. The questions are over, sir. Thank you very much.
Thank you, Dr. Yadav, for the question and answer session. Now may I request Mr. Prasijjo Kothakar for both of things. About Mr. Prasijjo.
Thank you, Dr. Satanmurgan, sir. Good morning, respected dignitaries. I, Prasujya Kothakar, on behalf of CSI and NIST and the entire organizing committee, convey my sincere thanks to Professor R.B.S. Yadav, sir, for such an informative and descriptive talk and giving us a deep insight on seismic hazard. It was a great honor to have you on board of us today, sir. Your lecture has showered tremendous knowledge upon us. Once again, thank you so much for sparing some time from your busy schedule and enlighten us with such an amazing talk. Thank you, sir.
Thank you.
I convey my gratitude to our respected director, sir, Professor G. Narahari Shastriji, for giving us the necessary permission to conduct this international virtual workshop. My sincere thanks goes to the chairperson of the session, Professor J.R. Kayal, sir, former Deputy General GSI, and the co-chairperson of the session, Dr. Yadav Barua, sir, Chief Scientist, CSI and NIST, for their continuous support and guidance in each and every step for the smooth conduction of this international workshop. Nevertheless, I thank the convener, Dr. Shantanu Barua, sir, Senior Scientist, CSI and NIST, for giving us such an amazing platform to interact with some prominent figures in the field of international seismology. At last but not the least, I thank all the participants across the globe for their active participation and the organizing committee for their tremendous effort and hard work making this international workshop a success. Thank you all. Love from India.
I